Okay, so hi everybody. Today we have Yibo Gao from MIT, and he's going to tell us about the canonical bijection between pipe dreams and bumpless pipe dreams.
Thank you very much, Pavel, for the invitation and introduction. I need to apologize for not being there with everyone in person, but I really hope to once travel becomes easier. So this is joint work with Daoji Huang, who was a student of Alan Knudsen, and she is currently a postdoc at Minnesota. So for the agenda, I'm going to first introduce Schubert polynomials and some combinatorial models to compute Schubert polynomials, and then just tell you the bijection. So I also want to apologize for the expert in this room because this talk is designed to be completely understandable and will have a lot of reviews for the experts. So at the same time, if you have any questions, feel free to interrupt me at any time. And for the second half of the talk, I'm going to tell you why we say that this bijection is canonical, because it's going to preserve Monk's rule on the pipe dreams and bumpless pipe dream, for which I will also tell you about. Okay, so this is the only slide that will have some geometry which is going to motivate Schubert polynomials. The flag variety as a set is the set of all chains of subspaces of dimension 1, 2, 3, ... n of your ambient vector space C to the n. So this is just a set for now, but it has algebraic and geometric structure, and it's a smooth projective variety. And it has a Bruhat decomposition, which decomposes the flag variety into the open Schubert cells. And these open Schubert cells are indexed by the permutations in Sn. If you take the closure, you get what's called the Schubert varieties, for which we denote as X sub I. And the classes of Schubert varieties, because of affine paving, form a C-linear basis of the cohomology ring of the flag variety, which is isomorphic to the coinvariant algebra. That is the polynomial ring in n variables modulo the ideal generated by the symmetric functions with no constant terms. Well, of course, if it has a constant term, then that will just generate the whole ring. And the Schubert polynomials are denoted by math frag of pi, indexed by permutations pi, are just certain nice polynomial representatives of the Schubert classes. So the Schubert polynomials can be defined recursively, well, by Lascaux and Schussen-Berger using this divided difference operator. So this divided difference operator, denoted by partial I, acts on the polynomials by this formula shown here. So partial I of f equals f minus si of f over xi minus x sub I plus 1. Here, si is a simple transposition that swaps the variables xi and xi plus 1. So as we can see, if xi equals xi plus 1, then f equals si of f. So this formula here, the numerator is always going to be divisible by the denominator. So it stays in the polynomial ring. And the Schubert polynomial can be defined recursively from top to bottom by this formula. So if pi is the longest permutation, n minus 1, and so on, up to 2, 1, then the Schubert polynomial, well, here I'm only introducing the single variable Schubert polynomial, and it's going to be x to the staircase shape, which means x1 to the n minus 1, x2 to the n minus 2, and so on, up to x sub n minus 1. And if pi is not the longest permutation, then it's going to have an ascent at some position I, or in other words, the length of pi is smaller than the length of pi times Si. So Si multiplied on the right means that you swap the index I and I plus 1. In that case, we already know the Schubert polynomial at the permutation pi Si, which has a longer length. And then the Schubert polynomial at pi is just this divided difference operator applied to the Schubert polynomial at pi Si. So here's an example of the Schubert polynomials in the symmetric group S3. So we can see that we start with the Schubert polynomial at 3 to 1 to be x1 squared x2. And if we multiply 3 to 1 by s2 on the right, then we get the permutation 3, 1, 2. And if we do this calculation, the Schubert polynomial at 3, 1, 2 should be partial 2 applied to the Schubert polynomial at 3 to 1, which is partial 2 applied to x1 squared x2, which is, well, x1 squared x2 minus Si of this, which is x1 squared x3 over x2 minus x3 equals x1 squared, as you can see here. So although x3 doesn't appear anywhere here, but it's sort of as a variable, it still exists and can be used for this calculation. The Schubert polynomial has the stability property, which means basically that if you start with the Schubert polynomial at 3 to 1, you can compute the Schubert polynomial at the identity to be 1. But if you start with the Schubert polynomial at 4, 3 to 1, or maybe at 2, 1, then you also compute the Schubert polynomial at the identity to be 1. More precisely, for m less than n and a smaller permutation pi in the, well, I mean a permutation pi in the smaller symmetric group, if we let iota to be the natural embedding of the symmetric group Sm into Sn, which, well, the Sm acts on the first m letters, then the Schubert polynomial at pi equals the Schubert polynomial at iota pi, which is a property that's not at all obvious from the definition, but it's going to be obvious from the combinatorial models. Because of this, we can assume all our permutations live in an infinite symmetric group. So you can think about this infinite symmetric group as, for example, bijections on the positive integers with all but finitely many fixed points, so that it actually lies in some big aspect. Another non-trivial property of the Schubert polynomial is that you can see the Schubert polynomials expand non-negatively into the monomials, which is also not obvious from the definition. But we'll talk about the combinatorial models that generates the Schubert polynomial. And the first one of them is called compatible sequence. So it's introduced by Billy Joe Stanley in 1993. For an infinite permutation pi, a reduced compatible sequence of pi is a 2 by L array of positive integers. Here, L is the Coxeter length of the permutation pi. So we index this 2 by L array as A and R, which are both L tuples, such that they satisfy these 4 conditions. So because these conditions are kind of important, so let me actually talk about these conditions. So the first one says that this A is a reduced word of the permutation pi. And then R is weakly increasing. R is also going to be smaller than the corresponding A's. And lastly, if we have a strict increase in A, then we must have a strict increase in R. Okay, so these are just some conditions that we'll come back to later. If we let RC of pi denote all the compatible sequences of pi, then the theorem says that for a permutation, its Schubert polynomial is the sum of weights of all the compatible sequences of pi. So the weight of a compatible sequence is the product of the xr's. So only the r's will count towards the weight. Okay, so let's do an example. So here are the conditions. If pi is 3 to 1, then it has two reduced words. So one is S1, S2, S1, and the other one is S2, S1, S2, which are two possible choices for this A. So if A equals 1 to 1, then I claim that there are no R's compatible with A. So why is that? So A is 1 here, and R is going to be weakly increasing and smaller than or equal to A. So this already forces R to be 1, 1, 1. However, the last condition says that if I have a strict increase in A, then I must have a strict increase in R. But I have a strict increase in A here, which contradicts this last condition. So I don't have any R's compatible with 1 to 1. Okay, but if A is 2, 1, 2, then we have this R equals 1, 1, 2 that's compatible with A. So similarly, the good R must be 1 when A is 1, just because R is less than or equal to A, and R is weakly increasing, so it forces the last coordinate, the first coordinate to be 1 as well. And finally, R is weakly increasing, and if A has a strict increase, then R has a strict increase and R is bounded by A, so the last coordinate must be 2. Okay. And the theorem by Bailey-Jokul-Stanley says that the Schubert polynomial of 3 to 1 equals x1 squared x2, which is actually given by definition that I took. So any questions?
Could you give an example for S4 for the longest element? What's the reduced word and what's the compatible sequence?
That's a very good question. Okay, so 4, 3, 2, 1. So let me think for 1 second. So the reduced word should be 3, 2, 1, 3, 2, 3. And the compatible sequence R is 1, 1, 1, 2, 2, 3.
Okay, thanks.
So the reason that I can come up with it is because of what I will tell you next, which is this other model called pipe dream, which is also called RC graphs. Here, the RC stands for reduced compatible. So they are essentially the same object as the reduced compatible sequence. Okay. So reduced pipe dream or an RC graph of a permutation pi is a filling of the square grid of the first quadrant by two kinds of tiles called either a bump tile or an elbow tile. And this is the cross tile that gives you the inversions of the permutation. So these pipes will form, so these tiles will form pipes, as you can see here, and we index each pipe by its column number. So the pipe, and for this permutation pi, it means that the pipe I that starts in column I will end at row pi of I. The reduced condition says that no two pipes will cross twice. So we have pictures like this, and we index each pipe by its column number. So this is pipe 1, this is pipe 2, pipe 3, and so on. And also recall that pi is an infinite permutation, so we in fact have all of these pipes afterwards will just go in this 45 angle. And this is like a tiling of sort of the infinite grid, but we just usually write it down in a staircase shape so that we omit the boring stuff afterwards. The weight of a pipe dream is given by the crossings, the row index of the crossing. So in this picture, we have two crossings in the first row, one crossing in the second row, and one crossing in the third row. So that corresponds to a weight of x1 squared, x2, x3. And the theorem by Bergeron and Bailey says that for permutation pi, its Schubert polynomial equals the sum of weights of all the pipe dreams. Okay. So I just mentioned that these are really the same combinatorial objects because there's a very natural bijection from pipe dreams to compatible sequences. Let's say I have a pipe dream, and then I'm going to associate a simple transposition S sub I plus j minus 1 to each cross tile at coordinate ij. So a pipe dream is like a wiring diagram. So there's a natural choice of a simple transposition for each crossing, which in this case is given by I plus j minus 1. And then I have a certain ordering of this crossing. So this ordering will be used again later. So the ordering is from top to bottom and right to left. So I first look at the very first row, and then I go from right to left. And then I look at the second row, and I go from right to left. So right and left is a little bit weird in this setting, but that's fine. Okay. So I'm going to read off the simple transpositions in this order, and the A's will be these simple transpositions, and the R's is going to be the row index. So let's look at an example here. So on the left-hand side, I have this picture from the last slide. So I'm going to read off the process in this order. So I first read this thing because it's in the first row and it's in the rightmost position. And it corresponds, so it's at coordinate 1, 3. So it corresponds to the simple transposition S3, and it's in row 1. So this column in the compatible sequence corresponds to this crossing tile. And next is this tile, which corresponds to S1 in row 1. And I have this cross, which corresponds to S4 in row 2. And finally, this cross, which corresponds to S3 in row 3. So if you remember the conditions from the reduced compatible sequences, it says that my A's will be a reduced word of pi. And then the R's are weakly increasing, which is obvious because I go from top to bottom. And the R's is less than or equal to A because I is always going to be less than or equal to I plus j minus 1. And finally, if I have a strict increase in A, then that means that I have to go to the next row because within each row, the value of A goes from right to left is decreasing. So if I have a strict increase in A, then I must go to the next row to have a strict increase in the R's. So it's really not hard to see that this is a bijection. Okay. Because of this reason, we'll actually consider the pipe dreams and compatible sequences to be the same object. And we'll denote both of them as the pipe dream of pi. And for an intrinsically different object, is a bumpless pipe dream that's introduced by namely Shimozono to study back-stable Schubert calculus. So their setting is much more general than this, but I'll just use whatever we need here. It is also, like the pipe dream, a filling of the first quadrant, but now we have 6 tiles, for which I call the R turn or the R tile, the J tile, the blank tile, the cross tile, and the vertical and the horizontal one. But the important thing is that there's no bump tiles, hence the name bumpless pipe dream. So they also form pipes that starts in column I and ends at row pi of I. We also index each pipe by its column number, as in the pipe dream case. So this is pipe 1 and then pipe 2. And the reduced condition says that no 2 pipes can cross twice.
Sorry, Yibo, I have a question.
Mm-hmm.
So somehow the picture is that now your path go from bottom to from this bottom bottom to right, and before you go from left to up.
Exactly,
Is there a reason for that, or just a?
I guess that's just standard somehow. Or you kind of need that just because you want to index your row still from 1 to 3 from the top. So you kind of have to do it this way. But that's a really good point. So the bumpless pipe dream, each pipe will travel up and then go to the right. While in the pipe dream, you travel down and go to the left.
I see. And just one more question is that is it true that a pipe dream must be a bumpless pipe dream? What is the connection now? Like,
what's the connection?
oh, okay, I guess you'll explain that later. Okay, sorry. Yeah, I'm sorry.
I didn't fully get the question. But they are both combinatorial objects that enumerate Schubert polynomials.
I see.
That's what this project is about. Okay. Any other questions? Yeah, but now the difference is that the weight of a bumpless pipe dream is given by the row index of the blank tiles instead of the cross tiles now. So in this picture, we have two blanks in the first row and one blank in the second row and a blank in the third row. And the weights correspondingly is x1 squared, x2, x3.
Okay. Yeah, sorry to interrupt again, but just to make sure I understand. So I guess it's even if we revert the picture so that they have the same index, pipe dream, a bumpless pipe dream is not a special case of pipe dream, right? No,
they are not. They do have some sort of different feeling to them.
Yeah.
So the whole point of this project is to tell you what is the bijection between these two objects, basically. All right, thank you. Thanks for the question. So a theorem by Lemma Shimozono, which really is in a much more general context, is that the Schubert polynomial is equals to the sum of weights of all the bumpless pipe dreams. By the way, I should also mention that this is, as before, a filling of the whole infinite grid. So you may wonder how I'm going to add the other pipes, and the answer is I add the other pipes here. So the pipes can be extended like that, and the other pipes will go like this. You can extend them to infinity. All right. Okay, so here is an example of the Schubert polynomial at 2143. And I have the pipe dream in the first row, the reduced compatible sequence in the second row, and the bumpless pipe dream in the third row. And the bijection has to be aligned like this just because this polynomial is multiplicity free. So this bijection has to be weight preserving, so it has to line up exactly like this. But one thing that you may notice is that sort of the multisets of the position of the cross tile and the multiset of the position of the blank tiles are not going to be the same. Just like that. So these multisets are not the same, and it's almost miraculous that they compute the same thing, especially in the double Schubert polynomial. Okay, so then I will just tell you what the bijection is, and we are going to construct this bijection by interpreting compatible sequences on the bumpless pipe dreams.
I'm sorry, can you say again? So the multisets are not the same, or are they?
Multisets are not the same.
Multisets of what?
The multiset of the positions of the crossings and the positions of the blank tiles are not the same. So if you write down the double version, you will have for the pipe dreams x1 minus y1 times x3 minus y1.
Okay.
For this guy, and for this guy, you have x1 minus y1 times x3 minus y3. So these are not the same. These are not the same thing. So one can only hope for a bijection in the single variable case, basically. But okay. So what I mean by a miraculous thing is that you sum them up in the double polynomial version, they are actually the same. Okay, so now I'm just going to tell you the bijection. So this is rather a long slide, but the procedure is really not that complicated. And we'll see an example very, very soon. So we start with a bumpless pipe dream, and the goal is to sort of decrease the length of this bumpless pipe dream by 1, and then split out an entry in the reduced compatible sequence. So this is what we call the pop operation on the bumpless pipe dream. So to do that, we are going to mark the first blank tile in the bumpless pipe dream by a label cross. So the first in the sense of the order that we have been defining, which is the top and the right position. So there's going to be a first a first blank tile in the bumpless pipe dream, and we let R be its row index. Okay. So the first sentence of this item will not make sense for now, but we have a blank tile here labeled by a cross, and because it's the rightmost by this property, it's the rightmost. So if we look at the tile right next to it, this tile cannot be a blank tile, or it cannot be a cross tile, because they cannot have any sort of edges looking like this, because then otherwise it won't form a pipe. So there's going to be a unique pipe P that passes through this position. So I index the row number by X here, and the column number by Y. So there's going to be a unique pipe that passes through this tile. And this unique pipe will either, so we index this pipe by P. And if P is less than or equal to Y, that means that this pipe is going to turn at some point where this P is less than or equal to Y. And otherwise, it can also go straight down, in which case we have P equals Y plus 1. Okay, so these are the two cases. And let's say if P is less than or equal to Y, which means that this pipe is going to turn at some point when we go to this step. Okay. So as you can see here, this pipe is going to turn at some point. And then we can do a column move to this pipe using this labeled blank tile, so that we put this pipe to go through this blank tile at position of the cross, and then we move the cross down like this. So you can see also some of the pipes in the middle need to be adjusted accordingly, but that's just a very easy procedure. And now this tile, this blank tile may not be the rightmost in this horizontally contiguous block of blank tile. So we need to move this cross all the way to the right until we cannot move it anymore. And then we are going to repeat the first step. Hopefully that makes sense. So at some point, we are going to be in the step 3 situation, where you have this pipe that goes straight down. This pipe, again, is the pipe that passes through, it's the unique pipe that passes through the right, that passes through the right coordinate of the marked position. Okay. So this is Y plus 1 here, Y here, which equals P. So in this case, the pipe Y must intersect the pipe P at some position. There's going to be a cross here, and we can use the blank tile that we label to resolve this crossing, thus deleting this cross and also reduce the length of the bumpless pipe dream by 1. So hopefully that will make sense, and we'll see an actual example very soon. And in this way, we obtain a bumpless pipe dream of the permutation as A times pi, where this A is either P minus 1 or Y, which is the same number here. And we write top of this bumpless pipe dream D by the pair A and R. Okay, so here's an actual example. So we start with this bumpless pipe dream, and we have the cross at this position. And then we look at the unique pipe that passes through the right of it. And then because it turns, then we need to droop this pipe like that and put the crosses here. Now it's not in the rightmost position of a contiguous block of blank tile, so we move it to the right. We move it to the right, and then we look at the unique pipe that passes to the right of it. It now goes straight down. So it must intersect this pipe at some crossing. And then we resolve this crossing by letting this pipe droop like that, and this pipe go like this. So we resolve the crossing. And then we have a pop value, which is 4, 1. So what does this 4, 1 mean? So 4 is a simple SA that you multiply it by. So the 4 is this value 4. So which is the S4 that you multiply the permutation. And then the 1 is the row index of the crosstalk that you start with. Okay, so this is just one iteration of this procedure. Any questions?
Sorry, maybe I see it wrong, but somehow I saw that the crossing on the left is not the empty picture on the right. Well, maybe it's the bijection is not done yet. I guess because you said it's a bijection of pipe dream to bumpless pipe dream, right? So it's supposed to convert the crossing, the weight of crossing to weight of the empty spot.
Oh, sorry. So this is one step of
just one step. I see.
On the bumpless pipe dream. So it's not. Got it. I haven't told you how to translate that to the pipe dream yet.
Got it.
Oh, I just saw there are some questions in the chat. Okay. Yeah. Okay. So someone apparently found the slides. Thank you. Okay. So we remark that each step of this operation is invertible, which means that we can uniquely recover the bumpless pipe dream D by the smaller bumpless pipe dream nabla D and the pop value. So again, this procedure starts with a bumpless pipe dream D, and then it gives you a smaller bumpless pipe dream nabla D, and it spits out a pair of value A and R. You can also do it in the other way. So it is possible that it doesn't exist, but if it exists, then it can be uniquely recovered. Okay, and now probably many of you can guess what the bijection is. So given a bumpless pipe dream D, we are going to do this pop operation as many times as we need. And each time we are going to spit out a pair of value A and R. And these together will form a reduced compatible sequence. And because the reduced compatible sequence and pipe dreams are in natural bijection, so this gives you the bijection that you actually need. So pictorially, oh yeah, so an example will be shown in a moment. So this map phi is going to be weight preserving between the bumpless pipe dream and the pipe dream just by construction. Just for consistency of notations, for a pipe dream, we'll also have the notation of a nabla D and the pop values. The nabla D will be the pipe dream where you just simply remove the first cross tile. And if this cross tile corresponds to the simple transposition SA and it's in row R, then we write pop D as A and R. Okay, so this will be clear in a moment. Okay, so here's an example. So we start with a bumpless pipe dream on the left hand side, and we do this pop procedure. Right? So we have a label here, as if you remember, and we look at the unique pipe that passes to the right of it, and because it turns, then we do the droop to let this pipe go like this, and we move the cross for the label here, and then we look at the pipes again, and then it intersects here, so we resolve this crossing. So this crossing is S3, which means that I go to this nabla D, and then the value for the AR is 3 and 1. So 3 means the transposition S3, and 1 means the first row. So in this picture, correspondingly, we add a crossing in the first row that corresponds to S3, which is this crossing. So basically, one step of this operation on the bumpless pipe dream will corresponds to a single crossing in the pipe dream. And then we do this procedure again. If you want to do it again, the step is simpler. So you have the crossing here, sorry, the mark here. And you look at this pipe and you resolve this crossing. So you get here, which means that the AR value is 1, 1. So you're going to add a crossing in the pipe dream picture in the first row, which corresponds to S1, which is this crossing. So one step in the bumpless pipe dream corresponds to one crossing in the pipe dream. And you can go on like this. So for 2, I'll give you this, and finally this. To reduce to the identity bumpless pipe. Any question? All right. Oh, so here's just another example. Okay, so I should just mention that so in our paper, up to this point, including the introduction and preliminaries, proving the theorem, and so on, it's 6 pages. But the whole thing is close to 30 pages just because of what's coming next. So I'm going to tell you why we call this thing canonical, and for that I'm going to introduce monk-through, which is also a review for the experts. So monk-through tell you how you can multiply a Schubert polynomial by a linear functional, and on the right-hand side, you expand that into some non-negative linear combination of other Schubert polynomials of length 1 greater than pi. So I'm not going to go into details of what's written down here, but the coefficients are all going to be non-negative just by geometric reasons. If you do the same thing for, let's say, the Schubert polynomial at s of alpha minus 1 equals x1 plus x2 plus lower dot plus x alpha minus 1. And you can get another formula and you can subtract these two so you know how you can multiply the Schubert polynomial by a single variable x alpha. And then you can
what is TKL?
Oh, so TKL is the transposition of KL. So it's maybe
okay, cool. Thank
is
you.
more familiar. Good question. Yeah, okay. So by just manipulating this monk-through, you can also have another equivalent form of monk-through in this way. So I just want to multiply the Schubert polynomial by x alpha. And I have some other sums for which I just arrange so that the coefficients are non-negative. And this is the form that we are going to use. And the reason that we use this form is that if the right-hand side is a single term, then this is called the transition formula. If the sum on the left-hand side is empty, then this is called the co-transition. So just a remark for the expert, the transition formula is going to be very friendly with respect to bumpless pipe dream, and the co-transition formula is going to be very friendly with respect to the pipe dreams. So friendly in terms of how difficult it is to prove the Monk's formula combinatorially. So what do I mean by proving the Monk's formula combinatorially? It's just that, let's say we focus on the pipe dream, and we just want to prove this formula using the combinatorial model of pipe dreams. And so everything is now in pipe dream, which means that I will have bijection for the combinatorial objects on the left-hand side and the right-hand side. So I'm going to write this bijection in this way. So insertion by x alpha is a map from this term to the right-hand side, or in other words, the pipe dream of pi to this union of the pipe dream of these things. And I'm going to write mk beta to indicate a map from one of these terms to the right-hand side. Okay. And together, these maps form a bijection. Okay, so I should say that these things are already done for pipe dreams and bumpless pipe dreams, that such sort of bijection exists.
Are these bijections canonical in some sense?
Okay, so that's a very good question that I don't think it's easy to answer. I think so I think we can make it precise, but the way that these bijections are defined are fairly natural. So I think you could just use that to as like an interpretation of canonical somehow.
Okay.
But people have defined these things, and the procedures are pretty inaccurate. Okay, so our main theorem is the following. So the bijection phi that we define intertwines with these maps. So these maps can also be defined on bumpless pipe dream and on pipe dreams. And the main theorem is that our bijection preserves these maps that people have already defined. So that's why we call it canonical. All right. Okay. So let me actually tell you, it's not at all hard to define some bijection between pipe dreams and bumpless pipe dreams. So if you just want some way preserving bijection between pipe dreams and bumpless pipe dream, I don't care if they are sort of correct in the Schubert sense, then it's not hard to do. So why is that? So let's just define some bijections using the code transition. Okay. So the code transition formula, if you remember, says that the left-hand side there's a sum, and that sum is empty. And the exact formulation is here that I will actually go through. So if you want a code transition formula for a permutation pi, then you need to choose a specific index alpha for this pi, such that there are no k less than alpha, such that the length of pi times the transposition k alpha is the length of pi plus 1. Okay. So for example, you can always choose alpha to be 1, because if you choose alpha to be 1, then there are just no k smaller than alpha. And in that case, you'll get a formula that looking like this. But there are also other choices that one can make. So for example, if pi is this permutation, you can choose alpha to be 1, and you can also choose alpha to be 2. If alpha is 2, then you don't have any k less than alpha. Well, okay, so if you have such k, then k must be 1. But if you swap the 4 and 2, then the length actually decreases instead of increases. Okay. So you still don't have such k less than alpha satisfy this condition, which means that you have multiple choices of alpha. So now what I'm going to do is fixing a family of choices alpha for all the permutation phi. I'm going to fix a family of choices for all the permutation phi, and then I'm going to define a way preserving bijection between the bumpless pipe dream and the pipe dream by reverse induction on the length of pi, assuming that we already have those bijections for Monk's rule in the literature. So how is that going to work is that we know this bijection for pi equals W0, which is the longest permutation by definition. And then we are going to use reverse induction, which means that we have, so things here have a longer length. So we have a bijection between the bumpless pipe dream and the pipe dream on the right-hand side of this. And we can use the bijection in terms of Monk's rule to translate that bijection to the left-hand side. And then we can get some bijection between the bumpless pipe dream and the pipe dream for the permutation. Okay, I hope that makes sense. Please let me know if there are any questions. So, okay, so the conclusion of this procedure is that for any choices, you will have a bijection, which means that theoretically you can have an infinite amount of bijections, or rather a family of bijections, just using the code transition form. Oh, I should also mention that you cannot do induction instead of reverse induction. Why is that? If you do induction, which means that you already have some bijection here, and I want to translate that bijection to the right-hand side, and that will create some problem because each of these pi times the transposition alpha L may arise from other permutation pi, and you need to show there's some sort of compatibility going on. But if you go this direction, then you don't need to show that. So alternatively, you can also use co-transition. You can also use transition, not co-transition, and you do the induction from left to right. Okay. But either way, you are going to have potentially many bijections. But our theorem says that
in the formula, if pi is in a sum, then all permutations on the right-hand side are also in a sum, right? Not in, you never increase n by multiplying by these t.
You increase n. You can increase.
You can?
You can. You can increase n.
No, but then how would your reverse induction work?
You can still, because things here, I mean, if you go this way, you don't increase n. I mean, so there, I think there are indeed some subtleties in terms of how these things can be defined. But theoretically, okay, so if you do transition, or maybe I should really take the example of transition to avoid the subtle problem that the problem mentioned, but that's a really, really good point. So if you do transition, you go this direction and you don't deal with that problem. But yeah, but thank you for the question. But either way, our main theorem says that all these bijections are just the same bijection, and it's the correct bijection that you need, because our bijection preserves monthly. So that's why I said it's a unifies all approaches to define bijection via any versions of that. Okay, so I can tell you a little bit about Monk's rule. Wait, so sorry, Paul. So when should I end?
Just it's 10:50 or sorry, that's 50 okay. Or 55.
Okay, so I can tell you a little bit about how Monk's rule work on pipe dreams and bumpless pipe dream. Okay, so I'm going to define this map M of K beta. So how it's going to be defined is I start with some pipe dream B, and then I will need to go to the right-hand side, which is some union of collections of pipe dreams. But the idea should be somehow pretty straightforward. So there's going to be a cross tile that's responsible for the transposition K beta. I'm going to make it into an elbow tile and then search towards the right and make the first elbow tile into a cross tile. So remember that we always keep the weights. We keep the weight to be the same. So we delete a cross tile in this row and we have to add back a cross tile in this row. But what is the danger of adding a new cross tile is that this cross tile may create a double crossing with another cross tile. And if that happens, then I need to make that the new cross tile into an elbow tile and then search towards its right and do the same thing and then repeat. So it's not easy to, it's not hard to show that this process terminates and you end up with something on the right side. So I'm not going to really say the details, but let me do an example here that can show you this Monk's rule can actually last for many steps. So let's say I'm going to delete this cross, and I search towards its right to add another crossing here. When I add this crossing, oh, sorry, it's already in this page. Yeah. So if I add this crossing, then that creates a double crossing with this cross. So I need to undo this crossing and then add another crossing here. If I add a crossing here, then that creates another double crossing with this cross tile. So I need to undo this. I need to undo this and then search towards its right to add another cross tile somewhere. So repeat this procedure. And this is the example to answer Pavel's last question, that you actually add a cross tile here to end your procedure, which means that you actually need this part. But in the end, you get some reduced part. And you have a similar story for the bumpless part. Let's say, so this is the map that I'm going to use to add a x4 into this page. And so as always, the actual map go in the vertical direction and sort of the intermediate step go like this. So I'm going to add x4 in the bumpless pipe dream, and then I need to droop this tile over. So this tile needs to be drooped here, and then because there's there's one less blank tile in the picture, so we have to create another blank tile in this row. So we droop this position, and then we cross here. So we droop this position, we cross here, but we have a double crossing with this cross and this cross. So as before, we undo this cross tile, and then we droop again. So we make this pipe go to this position, and then we cross here until it's reduced. So that's the process on bumpless pipe. So one remark that I want to make is that both of the Monk's rule on bumpless pipe dream and pipe dream will consist of those things called the basic Monk steps. And it's easy to construct examples where you have maybe 10 basic Monk steps for a pipe dream, but just one Monk step for a bumpless pipe dream, or vice versa. So the basic steps really don't correspond. So that's what makes this whole thing a little bit annoying to deal with, that you really have to think about things more globally instead of just deal with these basic steps. And okay, so I have some, oh yeah, so this is, again, the main theorem that line up in this way. So you have Monk's rule, and we have bijections between the left-hand side and the right-hand side in terms of both pipe dream and bumpless pipe. And our bijection between the bumpless pipe dreams and pipe dream is given by this phi in the vertical direction, and the maps that people have already defined for the Monk's rule are in the horizontal position, and the main theorem says that we have this commutative diagram. And there are some outlines of the proofs and some main technical lemma. So this is like 20% of the main technical lemma that looks like this. And thank you very much for your attention.
All right, thanks. Yeah, very nice. So let me